Okay, so let's look at, we'll kind of go further. If you remember, and towards the end of the last module, we were looking at the different database. So in this module, we'll start with giving you some example of what kind of, when we say the databases, what kind of data are actually there in the database. So we will look at I'll have an example of how the database look like. So when you are, so when we say you go for this EcoInvent database to get some data, what kind of data they collect? I told you that right now we are working on a project with EcoInvent trying to collect data for textile industry in India. So when we are trying to collect those data, what kind of data is actually usually show up? And these are mostly unit data. So we work on unit data. So if you look at these two tables that we have, so let's start with the table on the left hand side first. So here we have this is an example. Again, these are not the complete database. Again, this came from EcoInvent. This is from the EcoInvent data. I have just pulled two tables for you to illustrate some points. So if you look at this particular table on the left hand side, and we have most of this data we express in terms of the CO2 equivalent, and how we do that I will also show you example of that later in this particular in this class. But we express things in terms of like a CO2 equivalent. So if you look at the first kind of the table over here on the left hand side, here we have the energy, some energy data and some transport data. Now if you look at the energy data, so that's some of these are really interesting, and I would like encourage you to pay good attention to that. So if you look at this 1 kilowatt hour of electricity, all these three, whether you look at this, all these three data is for 1 kilowatt hour of electricity. But depending on where you are in the world, the data changes quite a bit. So if you are in Quebec, which is actually in Canada, so Quebec is in Canada, if you are just above the New England states of US, Montreal and Quebec, Quebec is a province is part of Canada, where Quebec also is a province which French is very popular. French is one of the official language there as well. So in terms of if you are in Quebec, your CO2 equivalent is 0.023 kilogram. To produce 1 kilowatt hour of electricity, your release in terms of the CO2 equivalent, the fossil release is 0.023 kg. But if you are in China, that becomes 0.98 kg. So that's all. That's almost what you remember, if you nearly more than 50 times, something around that, nearly less than 50 times. But it's in terms of that much high impact is there. And then in terms of US, it is slightly less than China, but much higher than Quebec. Now, if we had numbers for India, it will be again very similar to what we have for China. Now, why the numbers are different? Again, the why question. Why the numbers are so different? That's why when I was talking to you earlier that when you do the LCIA exercise, the energy mix of that particular region or the country is very important. Quebec, it's mostly hydro. It's mostly hydel power and some maybe nuclear, but mostly hydropower. So since Quebec is mostly hydropower, the impact is much less. In China, it's mostly thermal power. As in India, China is now going a lot in terms of China is building a lot of renewable energy systems as well. But when this data was collected with the data, the kind of data that we are looking at, my suspicion is that it's mostly thermal power. So that's why you see a lot of much higher impact. And because thermal power plant, remember we talked about that thermal power plant. It's a coal mining. Water, during the coal mining also you need water, during the thermal power plant you need a lot of water, and then all the emissions associated with that. So that's a lot of impact in terms of the thermal power plant. In USA, it's kind of in the middle because USA is a mix. You have some thermal and predominantly thermal in many places in US. US is a big, although Canada is bigger than US in terms of area, but in terms of its population, it's almost just as like a 1/10 of the US population. So it's very low number of people, and most of the people actually lives along the US border. So that's where most of the Canadian population is staying. So that's, but it's in US we have a thermal and then mixture, some nuclear, some other like a renewable energy as well. So, but it's mostly coming from, and US depends on where you are. If you are in New England, Massachusetts, or those Rhode Island and those places, you will have a better carbon footprint. You will have a better energy mix in terms of the environmental performance. But if you go to Texas and other places, you will have mostly like a gasoline, fossil fuel based energy. So that's the energy data. Now, similarly, if you look at the transport data. So in transport data, they have been mentioned in ton kilometer. So the first 4 data is in ton kilometer. So that's for freight, moving things around. The last 2 is for person kilometer in terms of a person in like a people traveling around. So in terms of ton kilometer, like for the plane, it's around 1.1 kg. So what does that mean? Ton kilometers. It means to move 1 ton of the freight by 1 kilometer. So you are taking 1 ton of freight over a distance of 1 kilometer. If you are taking it by plane, you are around 1.1. If you are taking it by freighter, which is you go on the ship, it's 0.010. So ship transport is much better in terms of the environmental footprint. If you are doing it on truck, it's 0.12, by train 0.048. So if you have to rank, say if somebody asks you which one is in terms of the transport of taking goods around in the world, which is the best in terms of environmental performance, it's the ships, those big marine ships taking things around. That's number 1, followed by the train, then the truck, and then the plane. And the plane comes out to be more than that. But in terms of person traveling, in terms of 1 person kilometer in plane, that means 1 person traveling a kilometer by taking a plane or by taking a car, as the numbers are here. They are pretty much similar. The car comes out to be a little bit higher than the plane. So because the plane, there are so many people can go in one plane. Car, maybe 2 to 3 people in a car. So based on that, it comes out to be much little bit less, but it's pretty much, if you do a statistics, probably it would be similar. So that's how in terms of the inventory data for energy and transport. Now if you look at on the right hand side, some of the examples for the material, and towards the end, towards the bottom of that, we have some example for end of life. So 1 meter cube of concrete, you have 260 CO2 fossil fuel. This is 1 meter cube of concrete. 1 kg of glass, 0.52. 1 kg of steel, like a primary steel, not the secondary. Secondary steel means you are producing a steel from a recycled steel. So that's your secondary steel. So 1 kg of primary steel, 1.9. Look at aluminum, or in India we say aluminum as well, aluminium. So, but 1 kg of aluminum, the primary production is 9.5 CO2 like in kg. So for 1 kg of aluminum, we have a release of 9.5 kg of CO2. That's the primary production. But if you go for a secondary production, it goes down to 1.3. So that's 1.3. It's almost like we are looking at 7.5 to 8 times reduction. So that's a lot of reduction in terms of when we go for secondary. So that's why if you look at recycling of like a waste material, if you have taken a solid waste course, or if you have observed the solid waste industry, you know that recycling of aluminum cans is considered like is done a lot. The reason for doing that is aluminum cans, when you go for the secondary aluminum can, amount of emissions is almost like 1/7 or to 1/8. Since emissions is less, what does that mean? The process is less intensive as well. So it's less costly. It's like 1/7 of a price, 1/7 or 1/6 of a price of making a new aluminum can from a recycled aluminum as opposed to go for the primary production. That's why you see a lot of aluminum being recycled. That's the logic. That's what you see over there. So then we have copper, 3.1 kg CO2 like carbon dioxide. Corrugated board packing, that's your corrugated cardboard used for packaging material, 1.1. Newspaper, 0.78. So these are different examples. HDPE, LDPE, PET, PP, PS, these are all different types of plastics. So in terms of PET, which is the highest recycled as well, we have 2.4 kg of CO2 per kg of PET. HDPE is less than that, so PET has more carbon footprint, more environmental footprint. And again, these are your CO2 equivalent. So all the environmental footprint has been converted to CO2 equivalent. So that's what you are looking at. All the environmental footprint, the different criteria has been converted to one unit. That's your CO2 equivalent. That is over there. So it's so 1 kg. So PET is in terms of polystyrene PS has the highest, which is 2.7, which you see at the end. So polystyrene is the highest, followed by PET. And polypropylene and LDPE, they are similar, and then the lowest one is the HDPE. PET is what you see in terms of the glass bottle, the water bottles. If you buy a say Aquafina, Kinley, or Bisleri, and those kind of water bottle, the bottle that you have, that's the PET bottle. And HDPE is what you buy when you go for this, when you buy this detergents or those like a Saffola, those oil and cooking oil and all that. That container is HDPE container. So those are, and then there are other usage as well. So but there are different carbon footprint, environmental footprint. In terms of things going to the landfill, if it's an inert waste, you have 0.010 kg of CO2. So municipal solid waste, almost double of that. Cardboard, kind of in the middle. Plastic waste, you see even much higher. Now why? These are the 4 different types of waste. Again, whenever you see these kind of data, just don't take the data by the face value. Always think like why the numbers are different. What is going on here? Why the municipal solid waste to landfill is almost twice of the inert waste? The reason for that is municipal solid waste, when you talk about municipal solid waste, it has a lot of organic material. Inert waste will have negligible organic material. It may have some heavy metals and other things present in there, which may eventually go to the leachate collection system, and that's why you see some impact. And of course there is some impact because the landfill operation has to happen. The roller has to move on top of the landfill for the compacting of the garbage. So there is an emissions associated with that. There will be a kind of dust coming out at the landfill site. So those things are of course being used. But in terms of municipal solid waste, but those things are common. It is common for all the 4 criteria. Those basic landfill operations are common, whether it's a inert waste, municipal solid waste, cardboard waste, or plastic waste. Municipal solid waste, since it carries a lot of organic material in a landfill environment will degrade. And when they degrade, they will produce methane because they are organic. They are supposed to produce methane. They are when they degrade. So methane has a greenhouse gas potential. So that's, and then you will have some, not only methane, there are other gases are produced, and that will also have an impact. So cardboard, again, cardboard is not easy to degrade, but it will have some degradation. That's why you see some impact like kind of in the middle of inert as well as the municipal solid waste. Plastic doesn't degrade, but the plastic has the problem is that it stays in the landfill for a very long time. And since it does not degrade, that means you have to kind of manage the landfill for a longer period of time, and that has a bigger environmental footprint associated with that. Plastic waste is a big problem in the world right now. It's actually, if you follow waste management, if you just Google plastic waste issues, and you will see lots and lots of news articles, videos, and other things out there. We are having a big problem, especially those of us who loves seafood. If you like seafood, if you like the fish from the oceans, and then most of those fish are getting contaminated by plastics, and that's not good for our health. So plastic is a big problem in terms of in terms of the waste management right now in the world. So that's how you have the database. That is the previous slide. This slide kind of showed you how the databases are available in the how the data is available in the database. Sorry, so the format in which the data is available. You saw everything was for 1, 1, 1, 1. That means unit, isn't it? Unitary method. Remember, we always go back to like 1 unit, 1 of this. So similarly here, if you want to do this life cycle stages of that CO2 inventory for the incandescent light bulb, we can again the same problem. Remember, we did the problem earlier where we had the amount per functional unit. We had that life cycle stage: manufacture and packaging, distribution, use, waste collection, end of life, and we use some of these numbers over there. So glass 2 to 228 grams, copper 12 grams, cardboard 232 grams. So this is how these numbers came, because we had the data for unit, then we multiplied by 10. So this is how we got the numbers coming out. So then you can calculate CO2 release per unit, because 220, this is per kg, we know the numbers. So we can calculate what is for the 228 grams. So that we get in terms of per functional unit, per unit, and then you get it per functional unit, and then you calculate for the total. That is the CO2, total CO2 equivalent coming out. So this is this much kg per functional unit of the material. So this is how you do your calculation. First, you find out what is the amount per functional unit that you need. You know CO2 kg per unit of the material per kg. Then since you need 228 grams, so you can take the 0.52 kg is per kg of the material, but here you need only 228, so you need to kind of do the math over here and you get 0.12. Similarly, you do it for others and then you find out the total CO2 per functional unit. So this is what actually we did in that particular exercise. Yeah, but these calculations, if you are using a LCIA software, these calculations are already done in the software. But again, as I said earlier, you as a researcher has to make sure that the calculations are correct. You cannot just say that the calculation is already done and this is what I got from the computer. You need to understand it and you need to make sure the calculations are correct. So that was in terms of our in terms of the data and the databases and the data, how the data is available in the database and how we use this database in terms of doing the calculation. Since again most of these are done by the computers, we kind of take it as a black box, but you need to be careful when doing that. So once you have all this data, now if you look at the last slide, the bottom part here, we have this 14.5 CO2 equivalent per functional unit. So now this has an impact. So we have an impact of, because of this carbon dioxide emissions or equivalent carbon, not only carbon dioxide, there are other factors in there as well, other emissions in there. They all has been put as a function as CO2. So because of that, there is an impact. So now we will look at how we do those impact assessment. So what that does mean, that this much CO2 equivalent is released to the atmosphere. Okay, that's great. This much CO2 is equivalent is released. So what? What negative impact or what kind of impact it has on the environment? And when we say environment, environment is a big thing. What kind of impact it has on certain parameters which we measure for water, wastewater, water, air, soil, and other factors which we will look at in when we look at this impact assessment, which is again this slide you saw earlier. This is the elementary flow. From the elementary flow, we had this input and output. From this input and output, we got the CO2 equivalent coming out. You just saw an example how we calculate that. Now we want to see with the CO2 equivalent that coming out, what kind of impact categories it is going to have an what kind of impact categories we need to consider. There are different impact categories we looked at. There was global warming, ozone layer depletion, change in land use, natural resource, acidification, eutrophication, photochemical, ozone generation, human toxicity, ecotoxicity. So all those different aspects are there, different impact categories are there, and then you can come up with a single score. That is what we talked about that earlier as well. It was very similar to when you have like a BSE Sensex or National Stock Exchange, those kind of stuff. So in terms of the impact categories, we'll look at, so in the different impact categories, we had this global warming. So global warming, so we'll look at some of these, the GHG emissions. Again, it's a like it has a global warming environmental mechanism. There is a cause and effect chain, because once you have the GHG emissions, that's your elementary flow. That leads to infrared radiative forcing. That's the first order effect. That can again further lead to increase in global temperature. That's the second order effect. Then can be sea level rise due to water expansion, because if there is an increase in global temperature, what happens? If you remember from thermal coefficient, when the water gets heated up, water will expand, isn't it? When you're looking at a small volume of water, that may not be a big deal, but when you're looking at a big volume of water, that also has some impact. So the sea level has a rise because of water expansion, and glaciers are also melting. So that we consider third level impact. And then similarly, like you will have a nth level impact where it has a damage to human health and ecosystem. So that's your nth order impact, nth order effect. So this is how different levels of impact that you have in terms of the greenhouse gas. And some different greenhouse gases takes different time and different level in terms of these different kind of impact. So infrared radiative forcing, we have taken it as a one indicator. We have taken a category indicator in terms of global warming as infrared radiative forcing, the first order effect that we have taken it for that. So elementary flow, again, in elementary flow, you have different impact categories where you have human toxicity, respiratory, ionization radiation, ozone layer, photochemical, and all that's then aquatic acidification, non-renewable energy, and all that. So these are called midpoints, and here this is a IMPACT2002 plus, which is a combined approach where we have both midpoint and endpoint kind of approach, and this is published on this particular paper, Joliet et al. 2003. And many places is still this is a popular. Again, as I said earlier, there are different approach being used in terms of impact assessment, and depending on which approach you are more comfortable with, people go with that. But this IMPACT 2002 plus and Recipe 2009, those are the most popular ones, and we'll look at Recipe 2009 as well later on in the course. So in terms of these are the midpoints, those are the impact categories for midpoints, and then from these midpoints we go to the endpoint. For example, we take certain of these criteria which leads to human health issues, some other criteria leads to the ecosystem quality, the global warming is related to the climate change, and then the last two is related to the resource use. So in terms of these in midpoint categories, this is your endpoint categories. These are also known as the damage categories. The midpoints are also known as the impact categories. So there are a lot of impact categories. So UNEP SETAC Life Cycle Initiative framework, if you remember, this is from that. So they have different from the LCIA result. Some may have based on our understanding of toxicity and all that associated with different emissions coming out. Some may lead to human toxicity problem, casualties, noise, photochemical oxidation, ozone, climate change, acidification. So these are different kind of impact over there. So these are our midpoint categories. But from these midpoint categories, when we go to the endpoint, to the damage category, so for one particular, for example, if you look at the in terms of casualties or casualties because it has a human health issues, it's a biotic natural environment, also biotic natural resources. So a lot of, in terms of the damage categories, one of the midpoint category could be in multiple damage category. So because they have a multiple kind of effect, it's very difficult to pinpoint which causes what. So as you can see, kind of in this particular area, it's totally kind of mixed up, where one particular midpoint category can end up in several damage categories. So then when we do that, we need to do what is known as the weighted, we need to do an allocation. So what in terms of midpoint category, when it goes to more than one damage category, in what ratio we need to divide those damage categories over there. So from the elementary flow, you have these human toxicity, respiratory effect, aquatic toxicity, eutrophication, global warming, non-renewable primary energy. So these are the impact kind of categories which is out there. So in terms of, let's look at some of these characterization scenarios. So where say if you have look at the global warming scenario, 1 kg of CO2 that is considered as the base. So if you look at 1 kg of methane, for 1 kg CO2, it is equivalent is of course 1 kg of CO2. But 1 kg of methane, the equivalent is 25 kg of CO2 equivalent. So it's 25 times more potent than CO2. In terms of N2O, it is 298 kg of CO2 per equivalent. So N2O, which is the nitrous oxide, it is it's like almost 12 times more potent than methane, and 298 times more potent than CO2. But you don't hear too much about N2O as you hear about the CO2 or methane emissions in terms of climate change, global warming. What's the reason for that? Again, these kind of questions should come to your mind when you are looking at these kind of slides. This type of question should come into mind. Why this doesn't shows up in our scientific literature that much? Because N2O, although it has a very high impact, N2O does not have it's not that much present into the environmental system. The release of N2O is at a very low level as opposed to release of methane or CO2. So that's the reason why you don't see this N2O being making news that much as you see the news being made in terms of methane release or in terms of the CO2 release into the environment. Some N2O does get released in say compost plants. Those places there are some papers, you will find some papers where they look at the N2O more closely. But in terms of a like a bigger picture situation, N2O, although it's very bad, it's when I say bad, it's not a technical term, but it has more harmful effects in terms of global warming impact. It has a more potent global warming impact as opposed to methane or CO2, but it's still you don't see that much of attention being paid to that. So there are some characterization model which is developed by IPCC, the International panel for climate change, and they do calculate the characterization factor. They do some characterization factor calculation. They used infrared radiative forcing generated by greenhouse gas, and with the different time horizons, 20 years, 100 years or 500 years. So at different time horizon they did that, and they look at two things: atmospheric lifetime, what is its like how long it will last in the atmosphere, and as well as the heat absorption, how much heat is absorbed from this particular global warming stuff. So let's look at this particular slide, and then we'll end this module. So here in terms of different types of, here on the left side are our different types of substance controlled by Montreal Protocol, perfluorinated compounds, carbon dioxide, methane, nitrous oxide. So their lifetime is there in terms of their lifetime. Methane 12 years, nitrous oxide 114 years, and for the different, we have different lifetime given over here. Radioactive, sorry, not radioactive, it's a radiative efficiency has been calculated for each one of them, and then we can calculate the global warming potential for that for different years based on the model that has been developed, and you can see different global warming potentials showing up. So CO2, of course, it will be all 1. So methane, as I said, for 100 years it's 25 times, and for 100 years nitrous oxide is 298 times. So there are, if you go for 20 years it becomes 72, 500 years it becomes 7.6 in terms of the potency as compared to carbon dioxide. And then there are others. As you can see, there are most of them are much higher, except few which are lower, and that's how you see that different impact is coming up. Again, we are not. I'm not going into the calculation of each one of these, how these were arrived at. So you need, if you're interested, you can look at this IPCC report, which towards the end of that report, towards the appendix, they do have calculations associated with that, how these numbers were calculated. But for this class, what you need to understand is, based on the different time horizon, the impact is different, and then with respect to carbon dioxide, we have like these are the ratio in terms of how much they have higher global warming potential as compared to CO2. CO2 is used as a base. So with that, we'll close this particular module, and then we will start looking at some of these LCIA, how life cycle impact assessment is done. So we kind of started looking at that, but we'll do some of those like examples, the practical examples of impact assessment towards the next module. So if you think about so far, we have started with in terms of LCA methodology, which have been covering, we covered part of it in week 4, and then in week 5 now we are looking at it. We started with the goal and scope definition, we looked at the function, functional unit, we looked at the LCIA inventory. Now once you have the LCIA inventory done, you have to try to understand, you have to start looking at the impact. So right now we are doing this impact assessment, and then after impact assessment, the last part will be the interpretation. And so once we do that, it will be a total cover of a broad LCA exercise steps. And then after that, I will also kind of give a quick overview of what are the key points of a good LCA. And then we'll move to other topics as we progress in the course. So thank you, and enjoy, like I'm enjoying teaching this course, so I hope you are enjoying watching it, and I look forward to seeing you again in the next module.